Stanford University.
Well, thank you very much, Robin. This is a little too much to take, I'm afraid, because I actually have to say that this is, at best, a status report. I'm just trying to figure this stuff out about active learning. Got interested in this topic maybe a year or a little over a year ago, and Robin's kind of been my guide through a dark, confusing process. Part of this was motivated by the sense that I wasn't getting what I wanted out of lecturing in classes, and that I didn't necessarily self-diagnose as a great and inspiring lecturer. I think I've given a few good talks, but I wouldn't call myself one of the great Stanford lecturers. And also, perhaps because out of some self-protective instinct, a growing sense that even great lecturers don't necessarily empower their students. And I think the most telling example of this for me was reflecting on all the seminars I'd been to in the weeks preceding this and realizing I don't remember very much of some very great seminars that I sat through. So I think that sitting and listening in a lecture format is much overrated, I guess. And it was in that spirit that I've spent some time trying to think about this. Now, those who know me either in the classroom or from interacting with me in research problems know that I'm kind of a hard ass. And I don't make it maybe as fun as I might to get started interacting with me. I think I set the bar kind of high for myself and others. And on the one hand, I think that can lead to good things. I'm now the proud father of 2 college-age kids, and I'm pretty proud of them. And I don't think I was so easy on them all the time. But we have a very strong relationship, and I do think that they appreciate that we got there eventually. Their friends who know me well probably feel somewhat the same way. Their friends who didn't know me very well, I think, probably think I'm kind of a bastard. So it's in that context that I imagine that there are many students who've been in my classes who aren't necessarily thinking of me as the friendliest of instructors they've run into. Okay, so it's in that context as a kind of a personal statement of where I'm coming from, that I want to go over a bunch of topics that have been rattling through my brain over the last year. And some of them I'll go into in some depth. In front of you is a little thing I call a clicker, because it reminds me of a TV remote, and it works by the same technology. And those of you who don't have one, there are a few at the table, so I really encourage you to move up and take a seat at the table. And we'll spend most of our time playing with these things, because I think it's a pretty interesting technology, one that I haven't really mastered yet, but I think you'll see it has a lot of potential. And there certainly are people around who've done more with it, and I think it's a growing opportunity on campus, especially in large lecture classes. These clickers allow a form of active learning that I'm pretty interested in. But there are other and maybe even more profound aspects of active learning. 2 that I think are very important but still struggling with are peer-based active learning, getting students to interact with their peers in a constructive way, and assessment-driven learning, which is a phrase I made up for this talk, by which I mean that exams can be more than just a chance to find out how well the students know something, but can also be an opportunity for them to learn a lot deeper understanding of the material. So here's an outline of what I want to say. I want to start by talking about what I see as the challenges of active learning, because I don't think this is an easy thing at all, at least for those of us who are not schooled in pedagogy. And despite the fact that I did win a Bing Award when I but after several years at Stanford for some work I did developing a laboratory course, which involved a lot of active learning. That context is certainly easier than large courses, and I think what I won that award for wasn't so much figuring out how to make it work in real time as taking the energy to develop some materials. So I actually feel a little bit like a fraud being called an award-winning teacher at Stanford, because I think what I won an award for was taking the initiative to write a bunch of materials. And I'm not sure that's the same thing as being a great instructor. I certainly would aspire to be one, and I'm hoping that by doing this, my instructional ability will improve. How do you make lectures active? We'll spend a lot of time on that, and that's what the clickers are on the table for. Peer learning environments, I'll spend some time talking about what I think I've learned about that, about how difficult it is, about the challenges of it, and about at least one case which I think is working quite well. Learning from assessment, the horror of exams. This is a topic that continues to challenge me because I do think exams, especially in large lecture classes, are first of all a great opportunity to learn, but more importantly, for introductory courses, they actually set the stage because if students don't master taking exams early on, there are a large number of classes they're going to have to be successful in their at least bachelor's education. Not all of them by any means, but certainly in the sciences a large fraction, which will demand that they be successful at exams. And so I think learning to take exams, while it could be seen as merely a means to an end, is nonetheless a very important means. I actually think it's an end in itself, but I guess that can be debated. And finally, I'll just end with some thoughts on this phrase, construction of knowledge, or the constructivist view of learning. I don't know much about it. I've read a little bit. I'm certainly no scholar of pedagogy or of this branch of pedagogy, but I think it's a really compelling metaphor that people learn best by, actually only learn by constructing their understanding in their own head, and that you can't relay that to them of whole cloth. It's got to be something that they put together thread by thread. And the best you can do is kind of help them to figure out how to knit the threads together. Okay, so some challenges. I just, not this is an exhaustive list, but just 4 things that I can put words on, nouns on. Authority is a real challenge to active learning, in my opinion, because the learner coming to Stanford, the student coming to Stanford, inevitably is looking at the faculty, the TAs, the materials we provide as authorities on the topic. And this leads to the attitude that this stuff, these people, are going to teach me something. And as I will contend in this talk, that's the furthest thing from the truth. That's not going to happen. Not in the simplistic sense of, if I come and am attentive, I will learn. I think relatively little learning will occur there, just as I go to seminars attentively and I come out barely able to remember what was said in the seminar. I mean, I get the overall gestalt of it, but I could not get up and tell you the story that I just heard. The next item I've identified is algorithmics, by which I mean that there is a right way to process this information and do whatever it is that this course is trying to teach you to do. By and large, that's not true. Certainly there are exceptions, okay? But that's the least interesting and least challenging part of a university education, is learning how to do the specific algorithmic things that need to be learned. You can learn how to count electrons in chemistry, or how to put together a proper Lewis dot structure. And that's important, and we make sure that people do that in introductory chemistry courses. But it isn't going to give them robust knowledge that goes beyond simply a skill that will be needed for more complex things. Another area that I think gets in the way is a sense that I'm getting distracted by this, as if it was the instructor's job, primarily, to make the material work for the student. Now, of course, it is our job to do that. I mean, our job is to sort of lay out and guide their inquiry. And I think this phrase, guided inquiry, like construction of learning, construction of knowledge, is a very useful metaphor. But it isn't primarily our job to do that. It is primarily the learner's job to do that. So when a student is distracted, we often, I think, conscientious teachers feel that somehow we've confused them, or we haven't taken them down the right path. If we only did a better job of laying out our lectures, the students would be less confused, less distracted. Yes, we probably could improve. But I think it's really important that we get away from trying to be perfectionists and keep the students undistracted and ready to learn and there, because that disempowers them from their greater responsibility to be doing that themselves. And I haven't really got my head around this one, but I think it's an important thing. And in some sense, this is a tough love thing. You know, yeah, there is just a really important role, and we should not take it away from the students to take responsibility for paying attention and figuring out what the point is themselves. It comes back to the construction of learning. And finally, as we all know who teach introductory science courses at Stanford, and I'm sure it's true not just in the sciences, we have a very heterogeneous population coming into the door to introductory classes. And I think this is particularly important in the freshman year, but it also applies to upperclassmen who are taking introductory courses. Often they're taking the introductory courses because they kind of put them off and they're not necessarily so central to at least what they thought they wanted to do when they came in. And so they really are coming from left field into some of these courses. They may have forgotten their Algebra 2, which is important to chemistry. Or they may not have thought about, you know, geometrical objects in three-dimensional space for a long time. Another thing which is absolutely essential to chemistry. Students coming to Stanford, I contend, though since I don't teach history and writing courses and literature courses, I probably would be disagreed with by those who do. But I contend that everyone who came to Stanford probably was at least walked through how to write a 3-paragraph essay about the origins of the American Revolution at least once in their high school career, the proverbial, essay. That's not true of solving difficult quantitative word problems. Word problems in Algebra 2 were often skipped over because either the instructor or the students hated them so much that they were something to be avoided. And yes, you had to do a few of them, but if the instructor was kind, not too much of your grade would be based on that. This is a really important skill, and there's an incredible heterogeneity in students' ability to do these kinds of things. I think of it as quantitative reading comprehension. It's not really algorithmic math at all. Our students are really good at that. That's tested for on the SAT. It's something more challenging. It's the numerical version of what the SAT verbal tests for. Okay. So those are just some of the challenges that we face trying to get students to be active learners. So I had this kind of eureka, and I know it's a bold statement. It's probably overdone, but I'm not going to teach anymore. I will guide and coach students to construct their own understanding. Now, this is an extreme statement, of course, and you'll hear me talk of myself as a teacher, or I'm teaching this class, or, okay, fine. But I think as a way to frame what it is that I want to try to explore with this mode of teaching, it's that I'm not going to teach anymore. And I think the athletic metaphor and the guiding metaphor, the tour guide metaphor, are actually really very powerful because they put you in the context that you've got somebody who wants to do it. I mean, you're outside of some required PE courses, people don't join a team and go out to play a sport because they have to, right? And you don't certainly pay a lot of money and go around the world and get a guide to show you the highlights of some high mountain or complex art history collection in a museum someplace in a culture you don't understand because you have to, right? So I think that's very helpful. It does two things. It gets, I think, the instructor in the right frame of mind of what their job is. It makes it clear that there are many ways to skin this cat. And it also keeps the instructor and hopefully the students, if this can be conveyed, and I'm not sure I'm very good at conveying this, but if it can be conveyed, I think it puts the students in the perspective that they're there because they want to be there. And I really, I understand they're required courses, but I just as soon ignore the fact that there are people taking my classes because they feel required to take them. And then finally, and I think this is the most difficult bit, and I'm still having trouble with it, and I sure don't find people like it, other instructors like it when I tell them this. Look, if we're going to have active learning in the classroom, we're not going to cover all the material, plain and simple. But we've got this wonderful textbook. I brought ours along, but I don't need to pull it out. You all know what introductory science textbooks look like. There are these thick things, and if the instructors are at all reasonable in their choice of the textbook, it's better than anything I'm going to say in lecture. I mean, it's been worked over and picked over, and I have my quibbles with the textbook. Anyone who's taught with me or taken a class from me knows that I'm not shy about pointing out the problems with the textbook. But I could not do better, right? Or I could iterate, maybe, from there. But, we're starting from some pretty good materials. And I don't think I want to try to duplicate that. I want to give up on the presumption that I will duplicate the textbook. And that's just not a popular thought with anybody. Okay, here's a very busy slide, which I showed in more or less this form to my Chem 30 class last year. We're on a 2-week learning cycle for the last several years in Chem 30, which is the introductory course in chemistry for people without any presumed background. Certainly, we have most students have had some chemistry, but I try to structure the class so that you could succeed in this class without any previous background in chemistry. Okay. So I've identified 10 things, and I want to walk through them and talk about some of the things that need to happen on a 2-week cycle. Some of these happen twice in that 2-week period, like currently we're doing problem sets twice during 2 weeks, once every week. Some things happen once every 2 weeks, the exam, which is actually fairly often by the standards of introductory classes. And that's a lot of work for the instructors, especially a lot of work for the TAs. So many of whom are here today, and I want to applaud you all for all the exams you've graded for me, because I give a lot of exams. Okay, so let's just walk through this. My view of, and it's really important once you say you're not going to teach everything that's in the textbook, is a really important thing to tell students is solitarily, on your own, you're going to read new material in the text. And frankly, that's just not emphasized enough. I mean, certainly a lot of high school teachers assume the material isn't getting read. But I think most of us assume that too, frankly. You're going to solitarily work problems, and to do that, you'll probably want to revisit the text. Because just like me sitting in that seminar on some very interesting aspect of science that I was totally into, they can be totally into reading this thing, doing number 1. But then when you ask them after the seminar, so what did he say about this? It's like, I don't know. I mean, I'm as guilty of that as my students. So revisiting the text is great, and that's why it's so nice that it's written down. You don't have to remember the details of what was said. You get to go back and look at it again. And I think this is sort of almost a dirty secret. It's like, yeah, of course they're going to flip back and figure out how to do the problems when they're actually trying to do the ones that they have to turn in for homework. Well, let's just acknowledge that. That's exactly what they should do. Okay? And why did they do one in the first place? Well, mostly to know where to turn back to. Number 3, in-class listening, questioning, and answering. Okay, we're going to come to this. This is sort of I hope, the fun bit of today. But I think that listening cannot be any more than a third of this activity. There has to be questioning both from the students and from the instructors. And more importantly, there really has to be the active act of answering. Of course, questioning can be active too, but it's very hard to make all the students ask questions. But you can make them all, or at least try to make them all, answer questions. So they're kind of a Socratic view of the interaction that we're having now, that we're not having right now. Okay? I thought, maybe I should actually use these clickers, and you'll see them in a minute, to create the kind of lecture my paradigm of a lecture today. And I thought, nah, it's lunchtime. I've never given this talk before. I'm going to punt. And not only that, it's sort of like an after-dinner talk. My job is more to entertain you today than to construct your learning. So we're just going to have fun with the clickers, and you'll see, hopefully, how they could be used, and how, at least, I'm trying to use them. Now, it turns out the clickers can be used for this, and I'm going to try to illustrate it today. But group constructing of arguments is perhaps a strange language to use. It comes back to this construction metaphor. I think it's really important, almost in the sense that lawyers use the word arguments, to construct thought processes and do it collectively. Now, we can do a little of that in lecture, and we'll try to do a little today. It's, there's only so much you can do in that context. Sections are certainly for that, but I think that most of the TAs in the room will admit it's too often not that. And I don't blame the TAs for that, because when I am in a discussion section with students or having office hours, it's damn hard to get the group to construct an understanding rather than to do what I'm doing right now. And finally, there's the hope, and a lot of literature out there of which I've skimmed barely the surface, that students will ad hoc form study groups that will be a positive constructing process in which they argue with each other. Though I think the TAs will admit that probably most of the time what they do is say, how do you do this problem? Oh, okay, you did it that way, I'll do it that way. And that's another challenge with active learning. And it's an important challenge. And it's why I emphasize this word solitary. Because at some point we have to come back to, this is, after all, your constructed knowledge, not something that you can share in a truly corporate sense with your buddies. So peer learning is tricky in that sense, because it's a means to an end. It is not the end. A lot of employers will tell us we want people who can work in teams and whatever, and that's great. To the extent that we convey that to our students, it's wonderful. I work in teams all the time. My research group is like that and so forth. But in the end, I stand up and give a talk, or a student writes a thesis, or a student goes out and gets a job, and we don't have to be everything. We don't have to be every man, every scientist, every woman. But we do have to have an individual identity of what is our intellectual self. And I don't think that peer learning should ever be confused with sort of a corporatization of the intellect. Exploring hard problems. This is, I think, a really important thing, especially at Stanford. We're a leading institution, and though we have a fairly diverse student body coming in, the goal, after all, of having a diverse student body coming in is that people going out will be able to do the hard work of cutting-edge intellectual work in whatever domain they pick. And not everybody's going to succeed in chemistry. We are going to have people who just get through it. That's okay. Hopefully they'll succeed at something. I mean, that's the goal of picking them. That's what the admissions office is after, right? But this is really important. We can't turn this into sort of a community college experience of just knowing how to work the problem. The hard problem is part of the intellectual experience of Stanford. Clarifying confusions in class, section, and office hours. Again, responsibility goes on the student to do this. I just don't understand. Why did you say this when you had previously told us that? That's their responsibility. And I think it's really important that as an active act, as something they actively do, rather than that they get done to them, they're responsible for clarifying. And then, of course, that's what office hours are for. I'm not making, this is nothing new, except that I'm just saying to the students, this is one of your 10 jobs. Number 7, rereading the text. You've done all this stuff. Go back and figure out, that text is going to look a lot different in the context of all this. And we got to make them we can't make them do it, but we've got to let them know that that's valuable. That's a part of active learning. Is to go back and critically say, what can I see in this that I didn't see there before? Taking and assessing one's performance on practice exams under as much of a real-world condition as possible. This is one of these just sort of pedestrian things that really matters. It's really important that students get good at taking exams. Otherwise, they're not getting the learning benefit I'd like exams to have. I don't want them just as assessment vehicles. But even if you just want them as assessment vehicles, you don't want to be assessing how terrified the student is. So this is really important, and I am proud to say that at least our department, and I'm sure every department on campus, makes a real point of making these available, serious last year's exams. By the way, they're always easier than the exams we give any given year. The TAs will know this. All the previous exams that we hand out are easier than the one we give the next day, or the exam time that week. It's just true. We make the exams harder every year. Finally, of course, taking the real exam. And I put it in red, and I'm highlighting, and I'm making a big deal about it because it's a big deal to the students. And so there's no point in us sort of acting like, oh yeah, and by the way, there'll be an exam on Wednesday. No, it's just, yeah, we might wish that they didn't worry about grades and they didn't worry about their performance. But actually, if we stop and we think about it, we're very careful about how we give grades. And we grade very, very carefully in the chemistry department. And I think we grade very, very, very reasonably, at least within each class. There may be some heterogeneity among classes. But each class is very conscientious about making sure that we are accurately telling the student what we want them to know from our grading process. And we're doing that almost entirely, not entirely, but almost entirely in the chemistry department based on exams, at least in the introductory courses. So why not make that a big deal? Why not make that the focus? And why not be honest about it? Now, this is sort of like my kids' friends who don't know me very well thinking I'm kind of a bastard. I'm not at all sure that I'm not perceived to be a bastard. And there are these wonderful people who teach with me who get to be the good cops on this. I write the exams, or at least I take responsibility for what's on the exam. And the TAs, and I'm seeing them all here, I hope have taken advantage of the opportunity to be the good cops with respect to this. I don't mind being the bad cop when it comes to this, but it is an essential thing in active learning and in making sure we're honest about what matters. And finally, and this has been a real interesting eye-opener for me, for years I've been trying to figure out how to get the best out of the performance that was on the exam, how the student can extract the most out of whatever happened. The natural instinct, particularly if you're struggling with the class, is, well, whatever happened, it's over. And I mean, I can't tell you how many weak students don't pick up their exams, for instance. Right? Or if they pick them up, they don't really have a good sense of what the problem was. Now, this is not everybody, but it's a significant subset. And I think it's exemplary of an important problem, which is that because this is in red, because it is so painful, because it is so stressful, it's natural to want to just put it out of mind. But you've just lost a huge amount of what was there to be had if you do that. And so clearly and as much as possible guiding students to revisit, to do postmortems on their exams is real important. Okay, enough of the sort of overview. You can see a lot of elements there. There are many, many ways to construct an introductory studies course in science. That's just one. It obviously has a high emphasis on frequent examination. Let's talk about lectures a little bit. I think it's a little more fun. And it's a little more active. So here are some concepts that came to me once I decided I wasn't going to teach and I wasn't going to cover all the material. Pick only key concepts and skills to highlight. Now, this isn't easy, and I don't claim that I've succeeded. I think my TAs have sat through lectures where I was not doing this, even as recently as, the last year. I'm sure there were plenty of lectures where I didn't pick the right skills and concepts to highlight. And I'm sure there are plenty of times when I rambled on, as I am right now, trying to make what I thought might be a good story, but wasn't very successful. Anyway, no matter how good it isn't good enough because it's not active. So, though I'm maybe preaching more than I am actually accomplishing this, I think the key is to punctuate lectures with actions, with challenges, and with arguments. Actions are what I heard one person say, the only way you can teach physics is by waving your hands a lot. And I enjoy when I can get my head around it and be enough of an exhibitionist, which is not natural, saying things like, well, what happens when gravity pulls on something? I mean, what happens when, and you drop your own book on the floor and then it just wakes people up. The waving of hands, the moving around. And for somebody like me who can be kind of a long-winded windbag, that it helps. And I find that it breaks me up. I'm not stuck on my script then. Challenge. This is the whole notion of asking questions, right, of the Socratic process. And argument. This is the active part of getting students in lecture to talk with each other and interact with each other, or the peer part. And none of these are easy, and the last one is really tough. But sometimes it works nicely. And I think a real enabler for this are these little clickers. And so, though it's a little overblown, I'll call it the power of the personal response system. Now, that sounds like I'm going to sell you on this thing, and you'll come away, I hope, interested. A caveat. I am not going to tell anybody they should use this. And there's a real simple reason. It's not ready for prime time yet. We have two guys sitting over here who've worked really hard on this, and they're going to make it work today, I hope. But every time I walk into the lecture hall, I'm worried, is it going to work? Okay? There are two computers being run right now. There are two screens and two projectors. And it's not easy. It's possible, but it puts a big burden on the instructor to do it any other way. So that's the caveat. I think someday this is going to be sort of routine. It'll be like an overhead projector in the room. but you know what we've been through with just one projector in PowerPoint, and you get there and you can't make the projector work and all that stuff, well, we're going to have that same problem. Anyone who tries this is going to have that problem duplicated. Okay? So I think there's a real challenge here as to chicken and egg. Is it worth it to figure out how to get this right? And certainly Marcelo is thinking about that problem. That's all I'll say. Okay. So here's an example of a PRS question, a personal response system question. PRS, I guess, is a trademark, so whatever. You put out some facts, and for this one, I don't need to give you much of a mini lecture. Okay, I don't think we have a whiteboard, so I'm not sure I can give you a mini lecture anyway. But I might have preceded this by talking through some concepts, by showing some examples, by doing a case. Probably something that wasn't exactly the same, but illustrated some concepts. In this case, it was what's called the unit factor method, an introductory sort of intro science thing about how you convert units. And so in this question, I want to know 1, the number 1, the Beatles' loneliest number, is equal to which of the following? Okay? So take a minute to think about this. Marcelo, we can go ahead and start. On the right-hand screen, you will see a bunch of blank squares. When somebody has an answer and they push a button, hopefully the number on the back of your transmitter, I think there are numbers on the back of the transmitter, will show up on the screen. First you have to turn them on, yeah. The red button. And the pointy end points to this thing right here. So when somebody has an answer, go ahead and point and try to click in. Okay, now you see there's a number up there. There's also sometimes errors. Okay. Oh, you're only giving me 5 choices? Oh, you keep adjusting it? Okay, great. Okay, so go ahead and let's, if you don't have a clicker, there's a couple more up here. See if you can't get your number to register. Now, I set a time, or Marcelo set a timer on this. I think he gave it a minute and a half. You could set whatever you want. In fact, it's easy. Can I get you to raise it by 30 seconds? Yep, it's fine. So you see, you can kind of play it by ear. This group is kind of slow. Students do figure this out, and very quickly you can see that, hey, the numbers aren't coming in very fast anymore, and I'm getting, nobody's doing anything. People are getting bored. Let's cut this off. I usually try to cut it off when there's 1 or 2 people who maybe still haven't, woken up and clicked in, because otherwise it just drags. But I'm not at all sure how to get calibrated on this group. So anybody still trying to click in that wants a few more seconds here? Okay, let's cut it off. So what you see is a histogram of the answers. We have a few people who liked 1. This is 25%. Can you flip this over to numbers? We can see actually how many people gave each answer. So we had 21 respondents. It looks like the room has got, how many clickers do we have? 40. Jeez, there's something wrong here, guys. We had 21 respondents, and 12 of them picked number 3, and a bunch of other people picked other answers. I think I'll leave the pure learning aspect of this for another question. We have a strong consensus for answer number 3, and the important point that I would make at this point, given that the group is clear that they like number 3, and it happens to be right if I remember correctly, yeah. Is that this funny-looking number is equal to 1. Okay? And that is not usually something that most kids coming into high school are used to. Okay? Now, some will be, but many, especially in the real beginning course, that's not a way of thinking that they're used to. And I like that kind of, discombobulation of that's 1. It is. It's equal to. It is the same as 1. Okay. So I won't go into the sort of the formalism of that. I think most people in the room know what that's Okay, here's another one. Now for this, let me back up. I'm going to need to give you a mini lecture. Unfortunately, I don't have a board. So just the facts you need to know are that atoms are made out of 3 elementary particles, protons, neutrons, and electrons. The atomic number is symbolized by capital Z, and it's the number of protons which have a charge of +1. The atomic mass number is symbolized by capital A, and it's the sum of the number of protons and neutrons. Neutrons have no charge. And then the electrons have a charge equal and opposite to protons -1. Okay? So now, with that information, and for those who aren't chemists, I apologize, but we'll get maybe a chance to revisit this one. Here's some facts. Calcium 40 is calcium, so it has a Z of 20. That means it has 20 protons. And it has an atomic mass number of 40. How many neutrons are in the ion calcium 40 plus 2? This thing right here. Okay, we only have 24 people. There's somebody not doing their homework here. But in any case, I'm gonna cut it off now. All right. Too many chemists. Too many chemists with clickers. Not enough other people. All right. So the point is that there are 40 particles. The mass number is the sum of the neutrons and protons. There are 40 neutrons and protons in this ion, and 20 of them are protons, so 20 must be neutrons. Now, here's another one, very similar. Selenium-79 has a Z of 34. That's selenium, and A is 79. How many electrons are in the ion selenium-79 minus 2? What do the? I think they are uniquely assigned to your number, if I'm not mistaken. Is that right, Marcelo? This is anonymous. I mean, this is not anonymous. We know whether you've answered. Everyone knows whether you've answered or not. We can change these numbers to be your name. Well, that's useful because then you don't have to remember your number. You can see your name go up. But the color, as we've coded it, doesn't say what your answer is. So the answer is completely. I mean, whether you're right or wrong is completely anonymous. There is sort of the umbrage. I mean, partly I'm annoyed that we've got 40 clickers in the room and we're still only up to 28. And so if this were a class, I can check to see, geez, is this the right number of people here? Something's wrong. But the color, typically, we're not trying to, this is the advantage over using a show of hands or holding up flashcards. You're not revealing your ignorance when you click in this way. People are obviously checking out this idea of doing it 2 and 3 times. Okay, let's close that out. All right, well, like I said, all the chemists have got the good stuff. So, yeah. Okay, we'll do one more, and on this one, let's have the chemists try to screw it up. There's a reason I'm asking for that. It's because I may not have given an appropriate set of questions today. I just pulled some out that were early in the curriculum where you didn't need to know very much to answer the questions. So this one is this question is called 3.01 times 10 to the 23rd of one, half a mole of the other. You know the expression, 6 of one, half a dozen of the other. Okay, so the facts are that neon has a Z of 10, and 1 mole is equal to 6.0221 times 10 to the 23rd. Question is, how many protons are in 9.03 times 10 to the 20 neon atoms? And if you're not sure how to do this, just pick an answer, because my goal here is to get a heterogeneity of answers. That's an editorial aside. Okay, we're going to give this 5 more seconds, and we're going to close it out, so just jump in there if you haven't already. Okay, go ahead. Oh, good. I know you just helped me out here. All right, so what I want you to do is turn to the nearest 3 people, identify a local group of 3, 4 people, whatever, no more than 4, and talk about how you solve this problem, okay? And what the steps are that help you to know what the right answer is, okay? And we'll take about a minute to do that. Okay, so I try to bring it to some closure, because we could go on indefinitely, and it's hard to know actually how long to wait at this stage. Some instructors that I've seen doing this in various formats will actually walk around the room and try to see where people are at, just to get a sense of when it's time to stop. This is obviously a relatively straight-ahead problem. There's a fact I forgot to tell you. Small m means 10 to the minus 3. Most people know that. But that should have been a fact up here, given that I didn't have all that laid out ahead of time. You hadn't done the reading and so forth. It's just lazy. Lazy. If you would just do the reading. Okay, so let's vote. Now everybody vote on their own. You're back to solo. Somebody's holding out on us. Yeah, but we only will take the last answer. Your last answer is the one that's getting recorded. Okay, actually, we're recording everything you said, but we're only going to show the last answer. Okay, let's close this out. All right, so we're homing in on 15 millimoles. So let's see how. So then a useful step usually is to kind of recapitulate this. You may get questions at this point from students. Say, how did they know? Whatever. Lots of opportunities because this action of doing something has caused people to wake up. And an important thing is you've punctuated the lecture or whatever format you want to use for that 50 minutes. You've punctuated it with having to think about something. And the anonymity, which is really important to Stanford students, as sad as that may sound, of not having to be on record with your peers as maybe not knowing the answer. So I would usually at this point, if there weren't questions and if we needed to move on, just recap the question by saying, okay, so we know that since Z is 10, there are 10 protons in each atom. We have this many atoms. That means we have 10 times that many protons. Do we have that answer available to us? No, this is 10 times less. This is equal. This is 100 times more. This is 1,000 times more. We don't have that answer. But we have a fact that a mole is equal to this number. Okay? So how much of a mole is this? Well, we have 1.5 times 10 to the minus 3 moles of neon atoms. So we need 10 times that many moles of protons. Well, we don't have that answer either. But we have millimoles. How much is a millimole? Well, that's 10 to the minus 3 moles. So 15 millimoles is 1.5 times 10 to the minus 3 moles times the 10 protons per atom. Okay. So that would be a chance to recapitulate that idea. Students find that's very useful. All of a sudden, what was just sort of flying high over their heads, like me listening to a seminar, and, oh, that went down so smooth. Yeah, that was great. I love that seminar. What did he say? Oh, I don't know. Now there's that moment of, oh, okay, now I see what, now it matters because I invested in answering that question, and I was confused, and now the answer means more to me. Okay, so that's the spirit of this. I want to switch gears real quickly. Peer learning environments. We just went through a little illustration of that. This was a method that I understand anyway, was developed by Eric Mazur to teach physics at Harvard. It's been widely used at Stanford in the physics department. Doug Osheroff first pointed this out to me, and I was initially skeptical, but over the years I slowly agreed to, or took it on to try it, and got together with Marcelo, who's been using it in the economics department. It's a nice way to bring not just active, but peer interactive learning into the lecture hall. But it's real limited. It's multiple choice. You can't ask really complicated questions. You can't work through very many multiple steps of something. You don't want to do too much math. That was about as much math as you want, that sort of thing. Okay. Now, I want to admit up front that peer learning environments are the most difficult thing that I've struggled with in the last year. I haven't had entire success with this. PRS, I think, offers a pretty good format in the lecture hall, but it's hard to know when you're asking the right level of question to generate the disparity of answers that can constructively result in peer learning experiences, as opposed to everybody just going, oh, I don't know, I mean, it could be this, it could be that. It's got to be at the right level, and it's not easy to hit it, even in this fairly simple format. The next thing is what we have done for so many years in laboratories. That is to write a guided inquiry document, a laboratory manual. You walk people through things. You ask questions. Consider what might be going on here. Well, you can do that in sections. It's tough. The TAs who've tried this with me know that it's not easy. TAs who've done labs know that it's not easy to do it in lab. It's even harder to do it in a discussion section. It's real easy to kick back to what I'm doing right now, which is pontificating. And so we've had mixed results with guided activities. There's a whole program set up by the NSF, led by a classmate of mine, Rick Moog at Franklin and Marshall College in Pennsylvania, and some of his peers, And they're now promulgating this method, which they call the really ungainly acronym POGLE, Process-Oriented Guided Inquiry Learning. And they actually teach whole classes in a discussion section format where the instructors try very hard not to tell anybody anything and get them to guide them through constructing their knowledge. It's tough, and I'm not sure how well it can work without a much greater investment than the investment in this technology. This is already hard to two computers that have to work, software that has to be loaded on one, presentation on the other, projectors, blah, 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 blah. Well, you try to do that, this guided inquiry stuff in a discussion section, I think it's a life commitment. And I just don't know how it's going to work, but we're going to keep playing with it over the next year. Postmortems on exams. A real neat thing happened on the way to the forum last fall. Rick Moog was coming to give a workshop. Some of you attended. Josh Radford and Nozomi and I were trying to figure out what to do, how to integrate postmortems on exams with this guided inquiry learning thing we were trying to do in sections. We'd always given back exams in sections the day after the exam was taken. And all of a sudden it just occurred, look, let's just hand out blank exams and have the students work the blank exam one more time, now not for credit, as a team. And though not everybody liked it, it was remarkably successful. So it's a form of peer learning where they are very invested in what they're doing. They still don't know what their grade is, but they've been worrying about it for the last 24 hours. And they sit down as a team and construct this. Many people commented, it was so much better than just getting my exam back. And they're really glad we held the exams back until after section was over and gave them out on the way out the door. I wouldn't have guessed it. We just tried it really just like, well, let's try this. It was remarkably successful. Study groups, advantages and pitfalls. We've been over this. TAs know this really well. It's so easy for a group of students to just tell each other the answers. The smart student dominates everything else. I think in a way that may be the best reason to keep at this. We school people in how to work in teams, and that's what this process orientation means. That's that ungainly part of the acronym of POGLE. School them in how to work together where the stronger student is not just telling everybody the answer. They all have to really understand the answer. If we can do that formally in section, perhaps study groups will have less of the pitfall problem. And I can be more comfortable promoting study groups as something other than just a way to get the homework done. Learning from assessments. Well, we got to quit here. So if exams are horrible, do them more often. Surprisingly, students like that because it lowers the threshold of pain for each exam. You know, if you screw one up, there's another one coming. The real problem with doing this is it's a lot of work for the instructors. It's a lot of work for the TAs. It's a big budgetary concern for the department long run. But I actually think more exams is really important. And I think just because it's an unattractive part, you know, on the surface of what we're doing is not a reason not to do it more often. And make a big deal about them. I've already talked about that. Reading comprehension. Make sure that the exams are not just sort of something you can see, oh, I see the algorithm in that, boom, 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 boom. I mean, it's very important. They hate it. Oh, they just tell me my exams are so hard. But it's really important that they have to extract and create an algorithm for themselves and not see an algorithm they did on their homework that they can just plug into to get it in. You can put a few of those on, but the body of the exam, you have to acknowledge and say it's not about using an existing algorithm. And what I think is really useful is to tell them, on the other hand, there are some tools. There are things that are going to be useful to you. One of them is something we call the reaction table. I like it a lot. I know my TAs have probably maybe don't necessarily share that enthusiasm. The unit factor conversion process we just went through at the beginning of this. There are a variety of tools, and if you cast them as tools, I make the analogy to Excel spreadsheets. Excel spreadsheet is not an algorithm for solving a problem. It's a tool for solving a problem. I think that's a useful distinction. Okay, finally, the point of what I want to say today is you need a balance between solitary and group work. Peer learning has to be very carefully understood, in my opinion. It's easy to mistake it. I think it's very easy to critique it, and I've heard that critique from plenty of scientists, that it's, you know, it's groupthink. Learning is hard work. Let's not run away from that. I think there's too much of making introductory study courses fun for their own sake. It's not easy. If it were easy, they wouldn't be paying all the money they're paying to be here. Hard work can be fun, but I won't make you smile. I won't try to make you smile. You may smile, but that's not my job. I'm going to acknowledge that you may not be enjoying yourself all the time here, and I'm going to be respectful of the fact that you may not be really grooving on this. And the terrain is complex. This is not something that if you just would obey or just work harder, you're necessarily going to get. This is like learning to do an athletic activity. A sense of balance, a sense of where you're at, trying and finding your own balance that isn't necessarily the one that I can give you. You've got to construct your own balance in doing the kind of challenging stuff that Stanford's about. So thank you all very much. Sorry I ran over a little.
Schedule, and I'm going to help run him through his Being on Track today. You may have seen already after that wonderful sales pitch from Chris that there is a workshop coming up on the PRS process that Marcelo and Jeremy are going to be hosting. So if you're interested in that, it's coming up on June 3rd. It's a faculty workshop. Again, I want to thank Chris. Thank you very much for the time you spent preparing this and the thought-provoking ideas. And he will stick around very briefly for a question or two.
Yes? Are there any undergraduates? Hands for undergraduates in the audience. One. I'm sorry. I know that our department demands more time of our undergraduates than most departments on campus. I'm sure we're not the only high demand time department on campus, and we're probably not the most demanding, but we're up there. But I'm not going to really make any apologies for it because I see an awful lot of other activities going on this campus. And I have to ask, at well over $30,000 a year, what's the point? And I may be at odds with the culture of Stanford, but I really think that people shouldn't necessarily be taking a whole pile of courses. Maybe 15 units is the most that many of our freshmen should be taking. But I do ask a lot. I ask a lot in that 2-week cycle. It's a lot of hours, but I think that's kind of what they're spending their money for. So I'm actually not, I know it can get to be too intense, but I don't see that as a real big problem here on this campus. And I'm sure there are people who would quarrel with me about it, but I'd want to see the budgets, especially for freshmen, of time spent. Oh, by the way, in answer to that, there's another thing. It takes a very disparate amount of time for different learners. And that's something the instructor needs to be aware of.
For more, please visit us at stanford.edu.